This video explains the dyadic product completely for solid mechanics. We begin with the vector dyad. Perform hand calculations. Compare it with dot products and contractions. Then build third-order and fourth-order tensors, projection tensors, spectral decomposition, and isotropic elasticity. The dyadic product of two vectors is written a tensor product B. It is the same as the column vector A multiplied by the row vector B transpose. In indicial notation, its ij component is ai times bj. Both indices remain free, so the result is a second-order tensor. Now calculate the dyadic product by hand. Each entry is one component of A multiplied by one component of B. The first row is 2 times each component of B. The second row is minus 1 times each component of B. And the third row is 3 times each component of B. The dyadic product is not commutative. Swapping the order changes the matrix. However, the transpose of a tensor B is B tensor O. That is a useful identity for checking signs and index order. The difference between a dot product and a dyadic product is the index structure. In a dot product, the repeated index is summed, and the result is a scalar. In a dyadic product, the indices remain free and the result is a second-order tensor. A dyadic tensor maps a vector in a very special way. A tensor B acting on C gives A times the scalar B dot C. For the chosen vector C, B dot C is 16. So the result is 16 times R. Direct matrix multiplication gives the same vector. The vector can also multiply from the left. The repeated index is now I. So the scalar factor is D dot A. For the chosen vector D, D dot A is 8. And the result is 8 times B. A central use of the dyadic product is the normal projection tensor. For a unit vector n, the tensor Pn equals n tensor n. It projects any vector onto the direction n. Because n is a unit vector, Pn squared equals Pn. This property is called idempotence. A plane with unit normal n has a normal projector, n tensor n. The tangential projector is the identity minus n tensor n. These two projectors split any vector into normal and tangential parts. This is used directly in contact mechanics, friction, boundary conditions, and traction decomposition. Stress acting on a plane normal produces a traction vector. The normal traction vector is the projection of traction along the normal. Using the dyadic product, this projection is n tensor n acting on the traction. The shear traction is obtained by the tangential projector. Identity minus n tensor n. Spectral decomposition is built from dyadic products. Each principal direction creates a projector. A symmetric tensor is reconstructed by adding the principal values multiplied by their corresponding projectors. For stress, the weights are the principal stresses. A vector dyad with a second-order tensor creates a third-order tensor. For Tijk equals AIAJK. The free indices or I, J, and K. The tensor can be displayed as 3 matrix slices. The first slice is 2 times A. The second slice is minus A. And the third slice is 3 times A. The reverse mixed product is also third order. But it is not the same tensor. A tensor product or has components Aij times AK. The vector tensor product has components AI times AJK. The order is the same, but the free indices occupy different slots. The dyadic product of two second-order tensors is fourth order. Its components are dijkl equals aij times bkl. The selected component calculations show that each fourth-order component is just one component of A multiplied by one component of B. The easiest way to visualize a fourth-order dyadic product is through blocks. For Dijkl equals Aijbkl. Each ij block is the matrix B scaled by Aij. For example, D12 is 2 times B, while D22 is -1 times B. A fourth-order dyadic product can act on a second-order tensor. If D equals a tensor B, then D:(x) equals A multiplied by the scalar B:(x). For x equal to the identity tensor, B:(I) is the trace of B, which is 6. So the result is 6 times A. The fourth-order dyad I tensor I has components delta ij delta kl. When it acts on a second-order tensor A, it extracts the trace of A and multiplies the identity tensor. For the numerical A, the trace is 4. So the result is 4 times the identity. The symmetric fourth-order identity maps any second-order tensor to its symmetric part. Substituting its definition and using the Kronecker deltas gives 1/2 of Aij plus Aji. For a symmetric small strain tensor, the result is the strain tensor itself. Dyadic products appear directly in isotropic linear elasticity. The stiffness tensor is lambda times identity tensor identity plus 2g times the symmetric fourth-order identity. When this fourth-order tensor acts on the symmetric strain tensor, the result is sigma ij equals lambda epsilon kk delta ij plus 2g epsilon ij. The dimensions are correct. Lambda and g have units of Pascal. Strain is dimensionless, and stress has units of Pascal. The general rule is simple. If one tensor has order P and another tensor has order Q, their dyadic product has order P plus Q. The component formula simply appends the indices of the second tensor after the indices of the first tensor. This comparison table is the safest way to avoid confusion. A dot product contracts indices and gives a scalar. A dyadic product preserves free indices and creates a higher-order tensor. Matrix products and double contractions are different operations from dyadic products. There are 3 major warnings. First, AIBI is not the same as AIBJ. Second, matrix multiplication is not the same as a dyadic product. Third, double contraction is not the same as a dyadic product. The difference is always visible in the free and repeated indices. The memory map is this. The vector dyadic product is AB transpose. Its components are AIBJ. When it acts on a vector, it gives A times B dot C. The projector N tensor N is a central example in mechanics. The dyad of 2 second-order tensors is fourth-order. In elasticity, the isotropic stiffness tensor is built from identity tensor identity and the symmetric fourth-order identity. The essential idea is that dyadic products keep indices free and build tensor structure.